device with unwanted vibration. Call that M1. Right, and then we have it attached to springs. We're lazy, so let's say that our total stiffness is K1. So let's call this K1 over 2 and K1 over 2. That makes sense? Yeah, makes our picture look pretty. Now what we want to do is, let's say we have this device with unwanted frequency and we want to drive, we don't want any frequency at a specific, we don't want any displacement at a specific frequency. Let's see if we can add a second mass down here. That will take all of the displacement, that we can transfer all of the displacement from this mass into our second mass at a specific frequency. That makes sense? So we still have all the energy in the system. We're just storing that energy in something that we don't care about.
So the two springs on the outer portions of mass 1, so since they're in parallel, are they not also in parallel with the spring connecting mass 2? Or is that considered like a different?
But the spring connected mass 2 is just from here to here, right? You could draw this. You could draw this whole system. It wouldn't look as pretty. You could draw the system like that if you wanted. Yeah, you see what I mean? It's a little harder to like conceptualize. So, but we have this device with unwanted vibrations, and we don't care how much this mass vibrates. So, if we have vibrations, we have to have a forced excitation, right? So let's consider that we have F naught sine of omega t. That work? Pretty simple. Okay, so how much does mass 2 need to be compared to mass 1? So a good assumption, right, when designing vibration dampers, right, is your auxiliary damper is between 1 and 5% of the total mass, right? So the mass at the top of Taipei 101 is about 2% of the total mass of the structure, a little bit under.
Is that including?
Yeah, so I mean, on Taipei 101, you have this building, you have this huge steel ball at the top. It's about 2% of the mass of the structure. It's very heavy, right? Because structures are very heavy. But you kind of have to make some assumptions, right? You gotta get some values to work with. So let's just say that, and I did that for a reason. So M1 is 20 kilograms. M2 is equal to 1 kilogram, 5%, right? K1 is equal to 20 kilonewtons, and F naught equal to 1 kilonewton, right? So what's the one thing that, what do we need to design? What parameter do we need to design for? K. Sorry, that probably should be K2. Oh, come on. So let's go ahead and design for K2. And you could do it the other way, right? You could set K2 and then design for your mass, but this is a slightly more direct approach. So equations of motion, right? We have two equations of motion. Let's go m1 x double dot of 1 plus k1 x1 plus k2 x1 minus x2 is equal to f naught sine of omega t. And then m2 x double dot of 2 plus k2 x2 minus x1 is equal to 0. Right, so we don't have any driving force on our bottom block, so it's equal to 0. That makes sense? Pretty good so far? All right, let's assume a solution. All right, so let's just assume a sinusoidal solution that looks like this. X I of t is equal to capital X I sine of omega t for I is equal to 1, 2. That makes sense? You have a displacement of x1, you have a displacement of x2, and we have this capital X. This is the term that we need to solve for. The sine of omega t, we already knew was going to be there, right? We have a sinusoidal solution. How can we get a solution to this?
Solve for x.
Solve for x, but that's a 3-step process. What's the first step? Yeah, take the Laplace, solve for x, convert back, right? So it's actually a different x. That is confusing now that I see that, but that's okay. Yeah, they're both big x's, but one is just like a block where everything's included. Like this x is just a block where everything's included. The other big X is the Laplace transform of x of t. I might change that in the notes. Or not. I don't know. Anyways, but using Laplace, which is pretty straightforward. I think we've done this one like 4 times. And no initial conditions. Right? We can get x1 is equal to k2 minus m2 omega squared, all multiplied by f naught over the common denominator k1 plus k2 minus m1 omega squared k2 minus m2 omega squared minus k2, 2. And then we can do the same for x2. But here we're just going to have k2 f naught over k1 plus k2 minus m1 omega squared k2 minus m2 omega squared minus k2 squared. Okay, so these are just our displacements. That makes sense? These are our displacements that give us our x of t. Pretty simple. We could actually solve for the displacements, but we don't actually want that. What we want to do is we want to mitigate the vibration in our system at one specific frequency. So to do that, let's go ahead and set our frequencies equal to each other, and let's try to set the displacement for m1 equals to 0. So first, we can get the natural frequency of m1, which is omega 1. We can solve for omega 1, right? So that's just omega 1 is equal to the square root of K1 over M1. Okay, so in order to estimate the movement of M1 for a given driven frequency omega, should we set the numerator to 0 for x1? Or should we set the denominator to 0 for x1?
No, the denominator is 0, 1
What is the number divided by 0?
Ooh. Undefined.
Thank you. But definitely not 0. But if the numerator, what if we set that to 0? 0, right? So we want to set the numerator to 0. What if we just make f0 equals 0? Does that work? Yeah, kind of trivial. Not really the point, though, right? I mean, mathematically it works perfectly, but not exactly what we want. So let's set displacement of m1 to 0, right? So we have k2 minus m2 omega squared equals 0. That makes sense? Now we have m2, what we need is k2, right? So k2 is equal to m2 omega squared. So note that this will force the frequency of the tuned vibration absorber to be the same as that of the system, right? So omega 1 is equal to omega 2, which is equal to the square root of k2 over m2. That makes sense? So we have a k now that we can use for that. So let's go ahead and plot these. Everybody likes plots, right? We need a plot that looks a little bit more intelligent. But to plot these, I want to normalize by my force, right? Just for plotting reasons. So that gives you your k. You can solve for k. For plotting reasons, normalize by force, right? So, sorry, normalize force by stiffness, just like we did before. Because what this does is gives you one plot that then you can use for a variety of systems, right? You just input your force, you input your stiffness, and then you can see what your K's are and what your response is going to be. Let's call that delta stiffness is equal to F naught over K1. So we can go ahead and play around with our two equations for x1 and x2, and that becomes x1 over delta of st is equal to 1 minus omega over omega 2 squared, 1 plus k2 over k1 omega over omega 1 squared, 1 minus omega over omega squared minus k2 over k1. So let's go ahead and plot this. And you can do the same thing for x2, but we don't really care about the displacement of x2 that much right now. Okay, so here is our displacement, x1 over delta st, for our system with an absorber and then without an absorber, right? So without an absorber, we enter into resonance at omega over omega 1. With an absorber, what happens?
Goes to 0.
It goes to 0 at which frequency?
1.
1. The original resonance frequency.